Hey guys, Mr. McKinney here, just doing our Unit 9 review video series. Unit 9 was on integrals. This is our second time going through integrals. Hopefully, most of this was review. There were only a couple of sections that were really new stuff. So, when you think about integrals, they're really just the opposite of derivatives. So you learned all these derivative rules. As long as you have the derivative rules memorized, then the integral rules should be fairly easy to memorize as well. It's just going opposite. So derivative of sine is cosine, so the integral of cosine is sine. Now, if we start with cosine, the derivative would have been negative sine. So if I want to do the integral of sine, it's going to end up being negative cosine. So think about where the negatives need to go. But I think it's easier to just memorize these 6 formulas and then think about how to apply them rather than trying to memorize 12 completely different formulas because they're really closely connected. Okay, so you have to make any integral problem look like one of these formulas or one of the other formulas that we have on our cheat sheet. So we don't have a divide by sine squared. We could potentially use U-substitution, but if we made U be sine, then we'd need a cosine somewhere, and we don't have any cosine. So all we do here is move the 3 out front, and then 1 over sine is the same as cosecant of x. So I just rewrite this as 3 times the integral of cosecant squared of x dx. Now I know that cosecant squared came from cotangent if I was doing the derivative. So when I do the integral, it's going to give me cotangent. But this is one of the ones that ends up with a negative. So when I look here, integral of cosecant has a negative. Because when I look at the original rules, the derivative of cotangent was negative cosecant squared. So when I take the integral here, it's just going to be negative 3 cotangent of x. Remember that anytime it's an indefinite integral, you need plus c, because this is just the antiderivative. It's the equation that will give you this 3 over sine squared of x if you take the derivative. So if I take the derivative of negative 3 cotangent, I'm going to get positive 3 cosecant squared, which is the same as 3 over sine squared. But I need that plus c because no matter what that constant is, when I take the derivative, it goes away. So anytime it's indefinite, make sure you have your plus c. Okay, I wanted to show you guys something here. Basically, both of these problems, or this is the same problem, but you can do it 2 different ways. And you'd need to use U-substitution because we don't have a rule for tangent times secant squared or secant squared times tangent. So depending on how we approach this, we might think about it as u equals tangent of x. Du would therefore be secant squared x dx. So if we do it that way, we've got u, and then we've got du. So it would just be the integral of u du, which would be u squared over 2 plus c. Plug my tangent of x back in. So it'd be tangent of x squared over 2 plus c. Now, I could have also rearranged it this way, and I could have said, well, let's make u be secant, because this could really be separated out as secant of x times secant of x, there's my secant squared, and then times tangent of x. Because if my u was secant, then my du would be secant of x, tangent of x, dx. So I can make it just be u du again. So it's still just the integral of u du, but I have a different u function. So I'd get u squared over 2 plus c. So instead of tangent squared over 2 plus c, I'd get secant squared of x over 2 plus c. Sorry, this should have been tangent squared of x over 2 plus c. Now, both of these answers are correct. And it seems strange that tangent squared over 2 and secant squared over 2 can be the same thing. And it has to do with this constant. And then it has to do with the identity rule having to do with tangent squared and secant squared. There's a plus 1 on one side. I don't remember which side it is. You can look it up. But real quick, I wanted to show you what the graph would look like. So as you can see, the graphs of tangent squared over 2 and secant squared over 2 are essentially the exact same thing. They've just been shifted up by a half on the secant squared graph. So a different constant could make these be exactly the same graph, which is why there's 2 equivalent answers. The constant would be different depending on the particular solution that you would end up finding. Okay. Again, we always have to make it match one of the formulas. So if it gets ugly, you're going to be using U-substitution. Now try to look for the derivative of one of them somewhere. So like, I don't know if I'm going to do U as secant, or U as secant squared, or U as tangent of x plus 1, or U as tangent of x plus 1 squared. It's not always obvious what to use as your U. So write out a couple different options and then figure out what du is for each one. So if I started with secant, then I'd need secant tangent. So I have a secant, but it's secant divided by tangent and it's tangent squared. So that's not going to work. If I made my u be secant squared, then my du would be like 2 secant of x and then times the derivative of secant, which would be secant tangent. I don't have all of this. Like if I take that secant squared away, I don't have any more secants, so that's not going to work. If I make my u be tangent, then my du would be secant squared of x dx. So this is looking good because I can make my secant squared of x dx be my du, and then I've got u squared on the bottom. So this 7 would go out front. I'd have 7 integral du over u squared, so I'd rewrite it as the integral of u to the negative 2 du. We've already done this problem, so I'm not going to finish it, but I just wanted to talk about how it's not always obvious what to use for u. Sometimes you just have to try different things. Okay. We also introduced one new rule in this unit, which is this one down at the bottom. You guys already should have known these rules, which is essentially the exact same thing. I'm not going to put both of them on the cheat sheet because they are the exact same rule. But you can do it with just a variable or a function as long as you have the derivative of that function. If your base is not e, you need to remember to divide by the ln of the base. Okay, so again, anytime you're doing an integral, it's got to perfectly match one of those formulas. So in this case, I'm going to be using U-substitution. When I see that exponential, I'm probably going to be trying to make it look like this. Integral of e to the u du. So my u would be 4x squared plus 3. My du would be 8x dx. So if I made this e to the u, I have my x and my dx, but I need an 8. So 8 on the inside, 1/8 on the outside. So then that could be rewritten as 1/8 integral of e to the u du. Now the integral of e to the u is easy because it's just e to the u. As long as the base is e, then it's the same thing. So 1/8 e to the u, and we just have to add our constant. E to the u is the easiest one to take the integral or the derivative of because it's the exact same thing. You just got to make sure you're using the chain rule. And u sub is the equivalent of the chain rule for integrating. Since it's an indefinite, I need to plug my u back in. So 1/8 e to the 4x squared plus 3 plus c. Again, if you have adding or subtracting, just split them up. And then for each of them, make sure you're using the appropriate integral rules. And you're going to have to use u sub. You might not have to write it out, but on this first one, we don't need any u sub because e to the x dx is on our formula sheet. So I'm going to take the integral of that. It's just going to be 3e to the x. Here, though, I do need to do u sub. Now, some of you guys are going to be able to do u sub in your head. Some of you guys are going to have to write it out. So if you want to do it in your head, you just need to think about what's the derivative of 2x. So the derivative of 2x would be 2 dx. So I need a 2 and a 1/2. And then it's going to be 1/2 e to the 2x. And then just do a quick check. If I took the derivative of e to the 2x, it'd be e to the 2x times 2. So that 2 and that 1/2 would cancel out and just give me the e to the 2x that I started with. 4 over e to the x we'd think about as 4 times e to the negative x dx. So the derivative of negative x would be negative dx. So I have to put a negative in somewhere, like on the inside and the outside. So then this one would become minus 4 e to the negative x, or you can make it minus 4 over e to the x, and we'd need plus c. So you don't necessarily have to show u substitution if you can do it in your head. So if you can recognize you need a factor of 2 and a negative here, you don't have to show all the work for u substitution, but you have to be able to do it one way or the other. Okay, just a reminder that we use the power rule for every exponent except the exponent of -1. Because the power rule says add 1 and divide by the new exponent. So x cubed over 3 plus c, x to the -1 over -1 plus c. But if I try to do the same rule here, if I add 1 to -1, I'm at x to the 0 divided by 0 plus c. This doesn't make any sense. This rule does not work for an exponent of -1. It works for any other exponent, just not -1 and not 0. I mean, I guess technically it works for 0 because then you're taking the integral of a constant, which is x. Anyway, ignore that. Make sure you guys have these rules memorized. They're not new. We already learned these ones. But when you see a fraction, you should be thinking, okay, there's a possibility that this is a natural log. The other possibility that you should be thinking about if you see a fraction inside an integral, like A, you might be able to write it as an exponent. So 1 over x squared, I just want to rewrite as x to the -2. The other thing we should be thinking about with fractions is potentially like tangent inverse, secant inverse, or sine inverse. And we'll get into that later on in this video series. So here I see a fraction, so I should be thinking ln potentially. So let's see if that works here. If I make my bottom bu, then my du would be 15 dx. I have a dx on the top and a constant, so I can work with that. I need to multiply by 5 on the inside, 1/5 on the outside. So then this becomes 1/5, there's my du over u. So then it's going to be 1/5 ln absolute value of u plus c. Since it's indefinite, I need to make sure I plug that back in. All right. Same idea here. When you see e to the x on the top and the bottom, that's probably an ln problem because the derivative of e to the x is e to the x. So I'm going to take this one on the bottom because when I take the derivative of that, the 1 goes away. And so then if I make u be e to the x plus 1, the derivative is just e to the x dx. So this is easy. It just becomes the integral of du over u. So ln absolute value of u plus c. So ln absolute value of e to the x plus 1 plus c. Okay. 9.2, we got into definite integrals, which is when you add limits in. When you don't have limits, you're just trying to find an equation that is the antiderivative. When you do have limits, you're not trying to find an equation anymore. This is going to be a value, and it's going to be equivalent to the area under the curve. So when we think about integrals, there's two main pieces of the family tree. You've got definite integrals, which is what this section is primarily about, where you have limits, and you have indefinite integrals where you don't have limits. Definite integrals, again, are the area under the curve. We say under, but really it's between the curve and the x-axis. Indefinite integrals are just anti-derivatives. Again, indefinite integrals are going to give you equations. Definite integrals are going to give you values. And this is when your calculator can help you. You can do Math 9 and just do it all on the calculator. Indefinite integrals, like there's software that'll help you do it, but on the AP exam, you won't have access to that. So you need to be able to do all this without a calculator. Some of these will be on the non-calculator also, but you should learn how to do it on the calculator. Now, when we take an indefinite integral, all of 9.1 was on general solutions. So you would have plus c. Now, we can find a particular solution and figure out what that c value is and plug it back in. So we're going to do that first, and then we're going to talk about area. So if I want a particular solution, it's giving me an initial condition and then the derivative. So to get from the derivative to the original, I'm going to take the integral. So the integral of f prime of x dx is going to be f of x plus c. So the integral of secant squared of x dx is tangent of x plus c. So that's my f of x, tangent of x plus c. And now I'm going to plug in my point. So tangent of pi over 4 plus, and then c equals, and then f of pi over 4 was -4. So tangent of pi over 4 should just be 1 plus c is -4. So c would be -5. C equals -5 is not the particular solution. Plugging it back in here and finding that f of x is tangent of x minus 5. That's your particular solution. It's also called a specific solution or the